eigenfunctions will be orthogonal, okay? Now, let me just say a few more things about convergence with respect to of functions, and that'll kind of help us build towards how the solutions that we're going to get from these sets of eigenfunctions can converge to a solution to the PDE that we're interested in. Okay, so we've already seen three notions of convergence, right? And we called them pointwise, uniform, which is the strongest, and L2 convergence. This is sort of the weakest, but it's easier to prove, right? So the first of these, right, fk of x is some sequence of functions from k equals 1 to infinity. This converges pointwise, okay, on S if fk of x goes to f of x for each x that lives in S, okay, your domain. Uniform is stronger, and it says that the infinity norm, okay, of fk minus f goes to 0, okay? And this is our uniform convergence condition. Implies uniform convergence, okay, of fk to f. And lastly, if the L2 norm converges to 0, this implies, not surprisingly, L2 convergence of fk to our function f, okay? And you can see Sheeran-Levy, section 7.2, for details, and I think they work through some examples on different functions that have uniform, but maybe not, sorry, pointwise, but maybe not uniform convergence, for instance. Okay. So this being said, right, it's helpful to work in spaces of functions that are not continuous, right? So that would be situations where we would only expect to have L2 convergence, right? So we may have, piecewise continuous functions. We may have functions with holes in them, right? This is a more flexible space of convergence to sort of worry about for proving particular things about how series are going to converge. Was there a question? I heard something bubble up, maybe. No? Okay. Okay, fine. So don't have a lot of time left. I'll try to get to a point here. Okay. So as I was saying, the reason is, right, that it's easier to prove things like existence of solutions in this case, right? It's way easier to say that I have a solution that L2 converges to solve my PDE and boundary conditions than it does that I have, a uniformly convergent solution to my PDE. Okay. So so we're going to work a lot in L2 to prove sort of a few more things about these generalized Fourier series, right? And this will just be, functions f that map a, b to the reals. We're working on real functions. And we'll say that f is measurable, okay? And its L2 norm is bounded, right? And so if the L2 norm of f is equal to 0, okay? Remember that this doesn't mean that f is equivalently 0, right? But it does mean that f of x is equal to 0 basically almost everywhere, right? You're just going to have these points where a set of measures 0 where it's not, where it's non-zero, right? So essentially, as we said before, right, for x in a and b, removing some set, let's call it, I don't know, t or something like that, where t is some set a to b that has measure 0, right? And this is usually good enough, right, to say that something's 0 in the L2 norm, okay? Now, the reason we're setting all this up, right, is to write the following theorem, and then I'll be done, okay? And I'll circle back to it next time. But all of this allows us to say the following. Essentially, we can say that the all of our L2 functions, okay, right, is complete, okay, in the L2 norm. Essentially, all Cauchy sequences converge. And to go along with this, basically every f that's in L2, okay, can be approximated in norm, okay, by continuous functions, okay? That is, right, there exists, right, some sequence of functions, f of k, such that they're all continuous, right, such that f minus f of k goes to 0 as k goes to infinity. So in other words, the continuous functions are dense in L2AB, okay? Now, why say all this? Well, essentially because what it means is that it's okay for us to work in the L2 norm, okay? Because the functions that are in the L2 norm, they're a broader class of functions, okay? But you can always take, a function that's defined in L2 and approximate it with some continuous function, okay, in terms of the L2 norm, to as high a degree of accuracy as you like, okay. So we haven't gone too far off the road essentially by working in L2, and the advantage that we have is that the things that we want to prove, like convergence of solutions, are going to be way easier to prove in L2 than having to worry about, very carefully dealing with continuity or continuous differentiability. And also the L2 norm and the L2 inner product are extremely convenient to work with, okay? So sorry, I went a bit over there. Are there questions about this before we conclude for today?
I had a couple questions.